So in the last class, we have derived the heat conduction equation in rectangular coordinates, and in rectangular coordinates, this was the equation we have developed: 1 by alpha del t by del tau equals to del square t by del x square plus del square t by del y square plus del square t by del z square plus q dash by k, where q dash is the rate of heat generated per unit volume per unit mass, t is the temperature, tau is the time, okay, alpha is the thermal diffusivity, okay, and q dash is rate of heat generated per unit volume. Okay, so this was we have seen in the last class. Now we can convert this equation into the cylindrical. We can write this equation in the cylindrical coordinates and spherical coordinates also. So in cylindrical coordinates, let's see how to write that. I am not going to derive the equation, but I will just give you simple intuition what the terms means in the equations. So let's start with the cylindrical coordinates. Cylindrical coordinates. So in cylindrical coordinates, let's draw a cylinder. So let's assume this is the axis, z axis, and this is the x axis, and this is x axis, this is y axis, and this is z axis. And suppose this is the radius. The radius of the cylinder is r. Suppose some point a p is here, okay, and we need to write the coordinates of this point p. So you can clearly see this is, suppose this is the origin. Suppose this p point, this is z distance above this, so z coordinate we can clearly write z coordinate is equal to z. So if you draw a perpendicular here, okay, so on the xy plane, you will get the point here, and this point, if you draw from the origin, this is the radius, right? Because from here, if you p point, you can p point is on the surface. If you drop a perpendicular on the xy plane, it will be on the ring, and the radius will be similarly like r. So suppose this r is making an angle phi from x-axis, okay, so we can write x coordinate. So if this is phi, the x coordinate is r cos phi. You can take a component, and y is equal to r sine phi. Okay, so this is y component. So this is the component, and using these components, if you put into the above equation, the rectangular coordinate equation, you will get a cylindrical coordinates. So I am just writing the final cylindrical coordinates because we are not going into the derivation. Okay, so it is 1 by alpha del t by del tau equals to del square t by del r square plus 1 by r del t by del r plus 1 by r square del square t by del phi square plus del square t by del c square plus q dash by k. So this is the cylindrical form, and this is the equation in the cylindrical coordinates. Okay, now we can write in the spherical coordinates also. Okay, so in spherical coordinates, let's draw a sphere having this is the y axis, this is z axis, and this is x axis. Okay, now suppose there is a point P here, and we need to write the coordinates of this point P. So let's join, this is, suppose this radius of this sphere is r, suppose radius of sphere is r, so this is r. So let's, this radius is making an angle theta with the z axis. Okay, it's a vertical angle, theta is making a r is making a theta angle with the vertical axis, that is z. Okay, so we can write z coordinate as r cos theta, right? And the second component r sin theta will be the perpendicular. If you, this is the xy plane, if you put a perpendicular here, this is the perpendicular, right? So this, let me draw with some other, so this is r sin theta. So suppose this r sin theta is making an angle phi with x axis. Okay, so you can take a component here. So if you take a component of this r sin theta, so this is r sin theta. Okay, so if you make a component, so you can take, and that will be your x. So x will be r sin theta cos phi, right? And y will be r sin theta sin phi, right? So I hope you understand this, how to write the coordinates in the spherical system. So if we convert, if we use these x, y, z into the rectangular coordinate system equation, we can get the spherical coordinate system equation. So we are not going to derive that, but I'm writing the final equation for you, and that is 1 by alpha del t by del tau equals to 1 by r square del by del r square del t by del r plus 1 by sin theta del by del theta sin theta del t by del theta plus 1 by sin square theta del square t by del phi square. Okay, so this whole term plus q dash by k. So this is the equation in the spherical coordinate system. Okay, now we'll see the linear one-dimensional steady state heat conduction. Linear one dimension steady state heat conduction. Okay, so in this we are going to discuss the steady state heat conduction without heat generation. Okay, so we are not going to take any heat generation inside the system. So that means that we are going to take q dash equals to 0. Okay, just a steady state, and steady state means del t by del tau is also we are going to take 0. Okay, so in one dimensional steady state system we are going to first consider a wall, plain wall. Okay, plain wall. So in this one, if we are going to consider both these, so we have seen the general heat conduction equation will become del square T equals to 0, right? Actually what we are going to do is finally we are going to calculate the heat flow. Okay, so we are going to derive what is the heat flow in the one dimension steady state heat conduction. Okay, and we are using only one dimension, that is only we are considering x direction, y and z we are considering constant. Okay, so this was the equation when we consider q dash equals to 0 and del t by del tau equals to 0. So let's consider a wall which is let's draw an axis first. So this is a temperature axis and this is x-axis. So let's draw a wall here. Suppose this is a wall, okay, at a distance x1. x1 from origin, so this is the origin, and this is x2, the right end point. And suppose the temperature here is T1 and temperature at this surface is T2. Okay, so we are going to derive what will be the heat flow. So we know that we can derive with the two method, है ना? So we are going to take first method. And what is the first method? So we know that del, so this equation, Fourier's equation, and we are considering only in one direction. So we can write as let's write in full first. Let's del 2t by del x square plus del 2t by del y square plus del 2t by del z square equals to 0. Now we are taking y and z as a constant, so this will be 0. Okay, so this will become del 2t by del x square equals to 0, right? So if it is this is equal to 0, that means del t by del x is constant, right? If you know the differential calculus, it will be coming like del t by del x is equal to constant. So suppose that constant is c. Del t by del x is c. Okay, again integrating, if you integrate again, then this will be so if y and z are constant, you can take del as a d, dt by dx is equal to c. This implies dt by dt equals to c into dx, and if you integrate, it will be like t equals to cx plus some constant d. Okay, so now here there are two constants. You need to find out the value of two constants, c and d. Okay, so you will apply boundary conditions. So at T is equal to temperature. So at T is equal to T1, T is equal to T1 at x equals to x1. So at inner surface, leftmost surface is x is equal to x1. So at x equals to x1, temperature is T1, and at x equals to x2, temperature is T2, right? So if you put all these two conditions in the above equation 1, you will get C value as T1 minus T2 divided by x1 minus x2. Okay, and D value you will get x2 into T1 minus x1 into T2, x2 minus x1. You can solve this, right? You will get C and D value. So temperature you can write. So final temperature, if you will calculate, you can write T equals to T2 minus T1 divided by x2 minus x1 into x plus x2 T1 minus x1 T1 divided x1 T2 divided by x2 minus x1. Okay, now if you have to write in the differential form, so you can write like this: T minus not differential, sorry, dimensionless form, T minus T1 divided by T2 minus T1. You can do some algebra, you can write like this: x minus x1 divided by x2 minus x1. So x2 minus x1, you can say L, length of the or width of the wall. Okay, and this is x. Okay, at a distance x from the origin. Okay, and where L is the thickness of the solid. Okay, so this is how the temperature distribution you can write, right? So now Q, you can find out Q equals to dq by d tau, right, is equal to minus Ka del T by del X, right? So now you can differentiate minus Ka del by del X, whatever this term is, temperature. So we have calculated there here this term, temperature. You can put it here. Okay, and finally when you differentiate, you will get minus Ka T2 minus T1 divided by x2 minus x1. So this is what we have learned also. Okay, so in a plane wall we can write like this: Q is equal to minus Ka T2 minus T1 divided by x2 minus x1. So this is for the plane wall. Okay, now we can derive for heat conduction in tubes, that is radial heat conduction through tubes. Okay. Okay, I forgot, we can do with one more method. Actually, let me complete that one. So another second method, you can arrive at this equation. And what is the second method? Second method was, so this was your temperature, this is x, this was x1, and this was x2. So let's take a small width here. Okay, let me use different color. Small width of tx. Okay, so we need to write a heat transfer equation through this width. And what will be that? Q equals to dq by dt d tau equals to minus Ka del T. Suppose the temperature change through this wall is del T by del temperature change is dt through this width dx. Okay, so if we integrate, so q into dx is equal to minus Ka dt. Okay, and q is constant because heat flow will be constant. So if you integrate both sides, so q you can take outside the integration, minus Ka, K is constant, A is constant, dt, and at temperature, the inner temperature at x1, at x equals to x1 temperature is T1, at x equals to x2 temperature is T2, right? So this will be q into x2 minus x1 equals to minus Ka T2 minus T1. So this will be q equals to minus Ka T2 minus T1 divided by x2 minus x1. So this will be the same as we have done in the first method, right? So let's move on to radial heat conduction through tubes. Okay, so radial heat conduction through tubes. So we are just assuming that the heat is flowing radially. Okay, so let's draw a figure. Suppose this is a cross section and this is a tube. Okay, and inner radius is r1, outer radius is r2. Okay, inner temperature here is T1, outer temperature is T2 at the surface. Okay, so we can do by calculus, that will be easy. So at a distance r, you can consider a small strip, consider small strip, this one, of width, you can consider dr. Okay, so now if you want to write the Fourier's law, so that will be q is equal to dq by d tau equals to minus ka dt. We can write d now, not partial, because we know the change in temperature is radially, right? So dt by dr, right? So q is equal to minus k. What is the a is the area, surface area. So surface area normal to the flow of heat. So surface area will be k into 2 pi r, and suppose the length is you can consider length l, 2 pi rl into dt by dr. Okay, so you can write q into dr divided by r equals to minus 2 pi kl dt. Okay, this will be the equation. This implies, now integrating both sides, you can get q, you can take as a constant and take outside, dr by r equals to minus 2 pi k into l is also constant, you can take these out and integrating dt. So at r equals to r1, temperature is T1. At r equals to r2, temperature is T2, right? So you can write 1 by r integration is log, or you can say ln, log base e, ln r, r1 to r2, right, minus 2 pi kl T2 minus T1, right? Now q equals to ln r2 by r1, this will be the minus 2 pi k l T1 minus T2 minus T1. Okay, so you can write q is equal to 2 pi k l T1 minus T2 divided by ln r2 by r1. So this is the heat conduction equation for tubes, cylindrical tubes. Okay, if you want to write in the form of like we have written in the plane wall, you can write like this: q equals to k am T1 minus T2 divided by r2 minus r1. You can write like this also, right? So if you compare both these, you can find the value of am, and am you will be getting 2 pi. So you can compare both these, so 2 pi l r2 minus r1 divided by ln r2 by r1. Okay, and this can be written as a2 minus a1 divided by ln a2 by a1, and therefore am is also called as logarithmic mean area. Okay, so you can write like this, and a2 is 2 pi r2l and A1 is 2 pi r1l. Okay, now in the next class we'll see the radial heat conduction through spherical shell. Okay, thank you.